So moving on to our intended learning outcome for this discussion, first on the list is to be familiar with the different properties of concrete. Actually, everything that we will study on this discussion we will be talking about the different materials that are being used to produce a pre-stress concrete. So first on those materials is the concrete, the most important part of pre-stress concrete, obviously. So our first goal will be to familiarize ourselves on the different properties of concrete. So next on the list is to be familiar with the different properties of non-pre-stressing reinforcement. Or if we will talk about in reinforced concrete design, usually we call this non-pre-stressing reinforcement as simply the steel reinforcement. So we will talk about that material as well on this discussion. Next on the list of our goal is to be familiar with the different properties of pre-stressing reinforcement. So if we have non-pre-stressing reinforcement, we also have pre-stressing reinforcement. And our last goal for this discussion is to be familiar with the different pre-stressing systems. So without further ado, let's address first our first goal, which is to be familiar with the different properties of concrete. So I suppose at this level, all of you are fourth year or fifth year already, and I suppose you are already acquainted with concrete, one of the most commonly used material in construction industry. So concrete looks like this. So from your construction materials and testing course, I know you have studied that concrete is composed of first cement, second water, third is coarse aggregates, which are usually gravel, and the last one is fine aggregates, which are usually sand. And additional to those components, sometimes we usually use or put admixtures to the concrete for different purposes, like for example, to retard its hardening time or to make it more workable or any other purpose depending on the goal. So concrete is a major constituent of all pre-stressed concrete elements. Obviously, this is the most important part of a pre-stressed concrete. Hence, its strength and long-term endurance have to be achieved through proper quality control and quality assurance at the production stage. So, since concrete is one of the most important part of a pre-stressed concrete element, we must usually ensure that it will have strength and endurance. And how can we achieve that strength and endurance? We have to be strict on ensuring that there will be proper quality control and proper quality assurance at the production stage of concrete. As we all know that the of strength and endurance of concrete usually depends on how it is made on the production stage. So there are parameters affecting the quality of concrete. Strength and endurance are two major qualities that are particularly important in pre-stressed concrete structures. Long-term detrimental effects can rapidly reduce the pre-stressing forces and could result in unexpected failure. Hence, measures have to be taken to ensure strict quality control and quality assurance at the various stages of production and construction as well as maintenance. So, we want to achieve that strength and endurance. We want our concrete that we will be using on making a pre-stressed concrete element to have the required strength and endurance for serving its intended purpose. So therefore, for us to be able to make sure that strength and endurance will be present on our concrete that we will be using on our pre-stressed concrete, uh, strict quality control and quality assurance at the various stages of production and construction as well as maintenance must be ensured. So how can we make a ideal, durable concrete. Or what are the qualities of an ideal, durable concrete? So first on the list is for a concrete to be ideal or durable, it must be resistant to weathering and chemicals. So can we ensure that our concrete will be resistant to weathering and chemicals? So these are the things that we must uh, strictly ensure to be present on our concrete for our concrete to be resistant to weathering and chemicals. First on the list is we must ensure that there is a appropriate cement type that will be used on the concrete. We must ensure that there is a low water cement ratio. We must ensure that there is a proper curing. We must ensure that our aggregate is alkali resistant. There are suitable admixture or we use super plasticizers or polymers admixtures, and there is air entrainment. So given that we already have all of this, therefore we can ensure that our uh, concrete will be ideal and durable together with controlled proportions of these things. So if you have these things together with controlled proportions, we can ensure that our concrete will be resistant to weathering and chemicals. Therefore, our concrete will be ideal or durable concrete. So another quality that our concrete must possess in order for it to be ideal or durable is it must be resistant to wear deterioration. So how can we ensure that it will be resistant to wear deterioration? Again, just like here, we must ensure that there is a low water cement ratio, there is proper curing, our concrete is dense or homogeneous, it has high strength, it has wear resisting aggregate, and has a good surface texture. So if we will have these things together with controlled material quality control, therefore we can ensure that our concrete will be resistant to wear deterioration, thereby producing an ideal, durable concrete. Another quality that our concrete must possess to be ideal or durable is it must possess the required strength. So how can we achieve that strength? We must have a good quality of base, low water cement ratio, optimal cement content, sound aggregate, grading and vibration, and low air content. So if we will have these things together with controlled placing and curing, therefore we can ensure that the required strength will be present on our concrete, thereby producing ideal and or durable concrete. Last thing, last but not the least, for our concrete to be ideal or durable is that it must be economical. So how can we ensure that our concrete is economical? It must have large maximum aggregate size, efficient grading, minimum slump, minimum cement content, optimal automated plant operation, admixtures and entrained air, and quality assurance uh, and control. So if we will have this together with controlled handling, we can ensure that our concrete will be economical, thereby producing ideal or durable concrete. Together with, most especially, there must be an appropriate cement type that will be used on our concrete, because we all know that there are different cement type depending on the use or purpose of the concrete. So there, we must use appropriate cement type in order for us to produce an ideal or durable concrete. So these are the things that we must ensure that our concrete possesses in order for it to be ideal or durable concrete that will be used in pre-stressing activities. So let's go to the different properties of hardened concrete. So when we say hardened concrete, these are concrete that already achieve its compressive strength. So this is not fresh concrete, it is hardened concrete. It already attained its compressive strength. So there are two categories of the properties of hardened concrete. The first one is the short term or instantaneous. So these are the properties of hardened concrete that are usually present on the concrete at the early stages of its life. So what are these? These are the strength in compression or the compressive strength, the tensile strength, the shear strength, and the stiffness as measured by the modulus of elasticity. So we can see here a concrete that is being tested using a universal testing machine to failure. So you can see the kind of failure the concrete experience. It experienced brittle fracture. It bursts when it can when it can no longer resist or support the load being applied to it. That is an example of that is how a brittle fracture occurs. So the second category of the properties of hardened concrete are the long term, which are creep and shrinkage. So these are the are properties that are usually present on the hardened concrete at the later part of its life. So it takes time for these things to occur on the hardened concrete. So this is one of the long-term properties of hardened concrete, which is the shrinkage. So this is what shrinkage usually looks like. So later on, we will discuss about all of these things. We will discuss all of this one by one. So let's start on the first short-term or instantaneous property, which is the compressive strength. So the compressive strength of concrete can be obtained up to 20,000 psi or more, depending on the type of mix, the properties of aggregate, and the time and quality of the curing. So we can produce actually a different magnitude of compressive strength of concrete depending on the type of the mix or the properties of aggregate and the time and quality of the curing up to a compressive strength value of 20,000 psi. Actually, those that kind of concrete that has this high amount of compressive strength usually is called high strength concrete. So those high strength concrete are usually the materials that are being used in pre-stressed concrete because a normal strength concrete cannot withstand the high amount or high intensity of stresses occurring on a pre-stressed concrete, especially coming from the pre-stressing reinforcement. Commercial production of concrete with ordinary aggregate is usually in the range 4,000 to 12,000 psi, with the most common concrete strengths being in the 6,000 psi level. So we can see uh, the common concrete strengths that is being produced commercially. Starting po, actually, it can start as low as 3,000 psi to 12,000 psi, or with usually the most common compressive strength being used is 6,000 psi, but on low-rise buildings we can use as low as 3,000 psi, especially on residential structures, and then we can go as high as 12,000 psi for high-rise buildings or structures like condominiums, especially on the column parts of a high-rise structure, because we know that one of the most stressed part of a structure, especially high-rise structures, are the columns of the structure. So it requires high compressive strength as high as 12,000 psi. The compressive strength FC prime or F prime C, whatever you want to call it, is based on standard 6-inch by 12-inch cylinders cured under standard laboratory conditions and tested at a specified rate of loading at 28 days of age. So can we know the compressive strength of a particular concrete, the FC prime? So usually we make a concrete cylinder with a dimension of 6-inch diameter. So the since it is a cylinder, the cross-sectional area is circular, and usually it has a diameter of 6-inch or 150 mm and a height of 12-inch or 300 mm. So that concrete cylinder is made, cured, and then tested at standard laboratory conditions and at a specified rate of loading at 28 days of age. So usually FC prime is the compressive strength that we have measured on the 28 days of age of the concrete cylinder. So the specifications for conducting that test on concrete cylinders can be found on Astm C39. So what is Astm C39? It is the standard test method for compressive strength of cylindrical concrete specimens. So actually you have to be familiar, and you have to familiarize with yourselves with this ASTM standards, ASTM C39, because uh, if you will be conducting thesis or capstone design which is related to concretes, so most of the time you will refer to this standards ASTM specification for the conducting of standard test method for compressive strength of concrete cylinders. For a strength test, ACI code specifies using the average of two cylinders from the same sample tested at the same age, which is usually 28 days. So we have this term which is called strength test. So what is strength test? So according to ACI, or actually you can also refer to our local code, the NSCP section 426.12.1.1, uh, the code defines what we call strength test. So the term strength test is defined by the code as the average of the strengths of at least two 150 by 300 cylinders. That is actually the 6-inch by 12-inch concrete cylinders. Or you can use actually the or at least three 100 by 200 cylinders made from the same sample of concrete and tested at 28 days or at test age designated for FC prime. So when we say strength test, it is a test usually conducted as the average of the strengths of at least two 150 by 300 cylinders. So strength tests always have a an average value of at least uh, two concrete cylinders. So that is the result of strength test as defined by the code. For the frequency of testing, the code specifies that the strength of an individual class of concrete can be considered satisfactory if, number one, the average of all sets of three consecutive strength tests equals or exceeds the required FC prime, and no individual strength test, which is the average of two cylinders, falls below the required FC prime by more than 3.5 megapascal or 500 psi. So you can refer to the ACI code or our local code NSCP for you to be able to know if the strength that you have measured in a particular strength test at a particular test age is already acceptable. Actually, you can refer to section 426.12.3.1 at letter B. It is specified there how can you tell that the concrete mixture that you are testing is already acceptable or not. So the first on the requirement on that provision is just like what I've said here. Uh, the average of any three consecutive strength tests equals or exceeds FC prime. So we can say that the concrete strength on the particular strength test that we have conducted is already acceptable if we will have uh, an average of any three consecutive strength tests equals or exceeds FC prime. So say for example, uh, we have conducted strength tests. So again, may I just remind you when we say strength test, it is always average of two concrete cylinders. Average of the strengths of at least two concrete cylinders. So say for example, the result of the first strength test is say for example 34 megapascal, meaning the average of the two concrete cylinders that we have tested is 34 megapascal, for example, for the first strength test. And then for the second strength test, we will have say for example 35 megapascal, and then the third is 36 megapascal. So if we will find the average of that three consecutive strength tests, we can see that its average is 35 megapascal. So let's say for example our FC prime is, say for example, uh, uh, 30 megapascal. Our target FC prime, say for example, is 30 megapascal. Since we already got an average of 35 megapascal on the consecutive strength test that we have conducted, therefore it exceeded our FC prime. Therefore, we can say that it is already acceptable, given that we will also satisfy the second requirement of the provision of the code, which states that no strength test falls below FC prime by more than 3.5 megapascal. So our FC prime is 30 megapascal, and obviously all of the strength tests that I have example are obviously more than the required compressive strength. So actually, we are not more concerned to satisfy this second part, because obviously it already satisfied the second part. So I will just make an example that will violate this second part. So say for example, uh, our FC prime is 35 megapascal. Or no, I will just make it 30 megapascal. Our FC prime is 30 megapascal. So say for example, the results of the strength test that we have conducted are, say for example, 25, 30, 35. 25 megapascal, 30 megapascal, and then 35 megapascal. So, according to this provision, there must be no individual strength test results that will fall by more than 3.5 megapascal lower than the FC prime that is required to us. So, our FC prime is 30 megapascal, and we have a result of 25 megapascal, which obviously is 3.5 megapascal, more than 3.5 megapascal lower than 30 megapascal. Actually, it is 5 megapascal lower than the FC prime that we are targeting, which is the 30 megapascal. So since it is lower by more than 3.5 megapascal to 30 megapascal, which is our target compressive strength, therefore it violates this second part of the provision. So therefore, we cannot say that the result of our strength test is already acceptable. So maybe we will need to test it again later on after, say for example, 7 days. But if we already achieve this, we already comply with these two provisions, we can say that the strength of our concrete is already acceptable. Therefore, we can no lo- we don't need to conduct any more tests on it, because it already satisfied this uh, accepting requirements. So, ano lang, just take note that the design FC prime should not be the average cylinder strength, but rather the minimum conceivable cylinder strength. So, like what I have said on the first example that I gave you, so for example, the results of the strength test are 35 megapascals, 36 megapascal, and 37 megapascal. So, what is the FC prime that we will use coming from those three results? So, we will not use the average of those three strength test results according to this statement. But we will use the lowest or the minimum strength test result that we had, which is obviously 30, 34. 34 ba yung sabi ko? 34, 35, 36. So, if the lowest strength test result is, say, for example, 34, so the FC prime that we will be using is 34, not the average of 34, 35, 36. So that is what is meant on this statement. We will not be using the average of the strength test results, but we will use the minimum strength test result as the FC prime for that particular uh, testing. So that's all for the compressive strength of concrete. So now we move on to the tensile strength of concrete. A good approximation for the tensile strength FCT of concrete is zero point 0.1 FC prime up to zero point 0.2 FC prime, or 10% to 20% of the compressive strength of concrete. So usually the tensile strength of concrete is just between that range, 10% to 20% of the FC prime. So you can notice that the tensile strength has a significantly low value compared to the compressive strength of the concrete. But the problem here is it is more difficult to measure tensile strength than compressive strength because of the gripping problems with testing machines. Because as we all know, if you want to test the compressive strength of a material, of a concrete, therefore we just have to subject it to compressive forces, obviously, because we want to test its compressive strength. So in the same manner, if you want to test the tensile strength of concrete, all you have to do is subject it to tensile forces to measure what is the amount of tensile forces it can withstand. So we just have to subject the concrete cylinder to tensile forces if you want to test its tensile capacity. So you can just imagine that for this particular photo, you can just imagine that if you want to test this concrete its tensile strength. If you want to test its tensile strength, we can just apply a tensile force on this end, on the other end. So we can just put a device here that will grip the concrete cylinder on this end and the other end, and then apply a tensile force. But the problem with that is there is a high chances of slippage. So the grip of the device on this concrete cylinder will have a high tendency of slippage, therefore affecting the integrity of the tensile strength test. So it will affect the tensile strength results of that particular tensile strength test. So it's really difficult to measure the tensile strength of concrete because of that difficulty on gripping. If we want to if we will subject this concrete to tensile forces, we will have difficulty of gripping this part of the concrete because it will tend to slip away, thereby resulting to uh, different tensile strength compared to the actual tensile strength of the concrete. So how can we resolve that particular problem? So there are a number of methods that are available for tension testing. The most commonly used method being the cylinder splitting or Brazilian test, which is actually this kind of test. The setup here that you can see here is actually the Brazilian test or the cylinder splitting test. Actually, you can find the specifications for that tensile strength test, the splitting tensile strength test of concrete cylinders on Astm C496 standard test method for splitting tensile strength of cylindrical concrete specimens. So you can find on that specification all of the things that you need to know on conducting the splitting tensile strength, especially the setup and how to compute the splitting tensile strength. For members subjected to bending, the value of the modulus of rupture F sub r rather than the tensile splitting strength is used in design because sometimes or before in reinforced concrete design, we usually assume that the tensile strength of a member that tends to bend uh, is actually the uh, modulus of rupture. We usually think of it that way, that that modulus of rupture is actually the tensile strength of concrete, but in reality it is not. Modulus of rupture and the tensile strength are two different things. Actually, modulus of rupture has a higher value compared to the tensile strength of uh, concrete. So if we will be talking about members subjected to bending, it is more appropriate to use the modulus of rupture rather than the tensile strength in the design of that bending member. The modulus of rupture is measured by testing to failure plain concrete beam 6-inch square in cross-section having a span of 18-inch and loaded at their third points. So this is how you can measure the modulus of rupture of a particular concrete specimen, you can find the procedures on ASTM C78, the standard test method for flexural strength of concrete using simple beam with third point loading. So you can find all of the specifications related to modulus of rupture test on this specification, especially the dimensions required for the specimen. So we usually use a specimen which has this dimension 6 by 6 by 6 inches, and then the span is 18 inches, and then it will be it will be something like simply supported on the setup. If you can look on the particular setup on ASTM C78, it will be set up something like a simply supported beam, and then it will be loaded with two loads. Uh, each of the load uh, is located at third points, and then uh, it will be compressed using that 2 points to until failure. So there is a designated way to measure the or calculate the modulus of rupture using those results from this test. So you can just refer to this ASTM standard for further information about the testing, the third point loading testing. The modulus of rupture has a higher value than the tensile splitting strength test, that just like what I've said here. In most cases, lightweight concrete has a lower tensile strength than does normal weight concrete. Actually, the symbol FCT, F sub CT, is actually the symbol for the uh, tensile strength of lightweight concrete, as you can see on the code provisions following here. So if you will refer from NSCP section 419.2.3, you can see how to compute the modulus of rupture of concrete. So this is the formula. But this is for uh, actually for normal weight concrete. We can just use lambda. If you can see here, we can use lambda just equal to 1. So you can just replace lambda here to by 1 to compute for the modulus of rupture of normal weight concrete. But if the concrete is lightweight concrete, you have to refer first on this particular provisions of the code. So actually, that is just similar to the code code provisions from ACI, because again, we all know that our local code adopted the international code. So much for tensile strength of concrete. Let's now move on to the shear strength of concrete. So actually, shear strength of concrete is more difficult to determine experimentally than the compressive and tensile tests because of the difficulty in isolating shear from other stresses. So again, just like what I've said on compressive strength, if we want to measure the compressive strength of concrete, we just have to subject it to compressive forces. If we want to subject it to or if you want to measure its tensile strength, we just have to subject it to tensile forces. But if you want to measure its shear strength, obviously we just have to subject it to purely shear stresses. But that is a major problem here because we cannot induce pure shear stresses on a concrete, because usually shear stresses occur together with other stresses like axial stresses, compressive stresses, tensile stresses, and or bending stresses, and so on. So we cannot isolate shear alone for us to be able to measure the shear strength of concrete. So because of that, there is a large variation on the shear strength values that we can get from the shear strength tests being conducted. So there is a significant variation in the true shear strength of a concrete that is being tested to the shear strength value that is being produced on a shear strength test. Shear strength control design is significant only in rare cases, since shear stresses must ordinarily be limited to continually lower values in order to protect protect the concrete from failure in diagonal tension. So if you can remember on reinforced concrete design, uh, we usually limit the value of the shear stress that will be experienced by our concrete element that we design to a certain magnitude to prevent failure from diagonal tension, which looks something like this. This is actually a diagonal tension. So you can see shear failure like this one, diagonal tension, usually occurs on supports like this one. On this case, we have a concrete beam and being supported by concrete column, and the shear stress, or the shear failure usually occurs at near the support. So why is that? Why is the shear failure usually occurs at the supports? So if you can remember, if say for example, if you have a simply supported beam supporting a uniformly distributed load, if you will draw the shear diagram of that particular simply supported beam, it will look something like a double inverted triangle with a maximum value of the shear occurring on the supports. So therefore, if there is a maximum shear at the supports, therefore, uh, chances are there is a very high chance of shear failure at the supports, just like what happened on this particular example here.